All right, so here's our third lecture. So it will be about linear regression. And this is our first standard machine learning technique for regression. I guess we've already seen k-nearest neighbor that can be used for regression, although it's not the most common use for that, so it's typically used for classification. What is more common is to use some regression technique like linear regression. Okay, so let's start by simply drawing on the board a picture that will illustrate what we're really doing when it comes to linear regression. Okay, so in linear regression, you start by having a data set. So here I've got some points, okay? And then the idea is that I'm trying to find the best line that comes as close as possible to those points. So here, the assumption is that when we're doing linear regression, we're restricting ourselves to the class of hypotheses that correspond to straight lines. So I'm going to search essentially for a line that comes as close as possible. So here's a possible solution, and now we're going to see essentially how we can find a line and how we can find a line that is optimal according to some notion. Okay, so now that we understand the problem intuitively, let's formalize things a little bit. We're going to formalize this by first saying that our data consists of some tuples that include some input features and then a target output. Okay, so here I'm going to use x in general to indicate the input features. And here, whenever I use an x that is bolded, it means that I've got a vector. Okay, so it means that I've got multiple features. So for instance, if we consider the problem of house valuation, right, x is going to be a vector of features that could indicate, for instance, the number of bathrooms, the number of bedrooms, the size of the house, and whether there's a finished basement, and so on. Okay, and then the target is going to be a numerical value, right, so a continuous value. In the case of house valuation, it's a price. Okay, so here it's not bolded because it's just a scalar. Okay, the other thing to realize that I'm calling this the target because this is the ground truth. Okay, so these are the values that we really would like to have the model predict correctly. So it does correspond to the ground truth. Now the problem here will be to find a hypothesis H that maps x to t, and then we're going to do this under the assumption that H is linear. So when we say that H is linear, what it really means is that we have a function that looks like this. We're going to take a weighted combination of the inputs where we have some weights, W1 up to Wm, that multiply the inputs. And then we also have another weight, W0, which is a constant. Okay, so it's a constant in the sense that it doesn't multiply any of the inputs. So in general, you see linear functions can always be represented in this fashion. So this is the, I guess, arithmetic equation for this. Now if I want to write this into matrix form or vector notation, then I can bundle all the weights into a vector W. Here I'm using W transpose to mean that it's going to be a row vector. And then I would multiply this row vector by another vector that's a column vector that includes a 1 and then x, which is the column vector of all the inputs. Okay, so the reason why there's a 1 here is because I need to multiply W0 by something. And in principle, I don't want to multiply it by any of the inputs, so I'm just going to multiply it by 1. Okay, so that's the main reason. Okay, so that's how we define the space of linear functions. And now the next question is, what's the best linear function? So we need some objective. So a natural objective will be to minimize some loss function. So for instance, I could consider the space, I could consider the Euclidean loss function, where I take essentially the squared distance by subtracting my prediction from the target. Yeah?
Sorry, what is y?
Okay, so y here is the output of my predictor, which in this case is a linear function. So it is essentially this linear combination. So it's the output. So in the context of house valuation, right, you have all the inputs like number of bathrooms, number of bedrooms, and so on. Multiply that by some weights, and then add this up together, and this will give you a prediction for the price. Okay, so y is essentially the predicted price that would come out from the predictor. And then we compare that to our target. So for a given house, right, where we observe that it got sold at a certain price, right, there's the ground truth. How much did this house get sold at? And that's the target.
So essentially we're just using h, the value, like the output of h.
So yeah, so here we can think of y as the output of h. Yeah. Yes?
So in the case of the real estate model, so x1 would be like number of bathrooms, and then what's t1?
So T1 would be, for instance, the price at which the house was sold. Right? So in house valuation, we have a bunch of inputs that are used to determine what might be the overall value of the house. And then there's a price at which it gets sold eventually. So T is a number, it's a scalar, that's the price of the house, and that's the ground truth.
Okay, so based on the fact that it has 2 bathrooms, what did it sell? Just on that one feature?
Well, so here we're going to consider more than one feature, right? So number of bathroom is one feature, but typically you see when you're shopping for a house or you're answering questions for a mortgage, right? Then you have to answer like easily 25 to 30 questions that correspond to all the features they're actually taking into account in their model. So yeah, so there would be lots of features. Think of this as a vector maybe of size 25 to 30.
Okay, so T1 is the price based on X1, just that one feature? Or?
So T1 is the price based on all of the features, not just one feature, all of the features, the entire vector X. So X is a vector.
So X1 is a vector?
X1 here is the first entry in the vector.
Okay.
Okay, and then I've got M entries. Yeah. Yes?
For the last equation, the xn is a scalar instead of a vector, right?
Oh, okay, good point. So here, yeah, I'm abusing a little bit notation. So here, x bolded, right, is a vector. Now the subscript n simply means that I'm looking at the nth data point in my data set. Okay, so imagine that I've got a data set. I've got in total capital N points in my data set. I index each one of them with small n, and that's essentially the index of that data point. Now within a data point, I have different values because a data point is really a vector. So here, yeah, I'm abusing a little bit notation because these subscripts really correspond to features, and this subscript here really corresponds to a data point. Yeah.
Why do we have to divide by 2?
Oh, very good question. So we're going to see this in a moment. So yeah, dividing by 2 is not needed in principle, right? So here, if the objective is to minimize that, multiplying by 0.5 doesn't change anything really, but we're going to see in a moment that when we do this, the derivation for the algorithm, there will be some term that cancel off, and then it will be convenient. But in theory, you're absolutely right, we do not need to divide by 2. Okay, so actually, with this set of slides, I posted on the course website a notation reference sheet. So let me just show you this briefly. So if you go to schedule and you scroll down to lecture 3, notation reference sheet. Yeah, so for this lecture and many of the following lectures, I'm going to reuse always more or less the same notation that I've summarized on this reference sheet. Okay, so as we discussed, we have the number of hypotheses, or sorry, we have H as a hypothesis and also the hypothesis space that's capital H. Now with respect to data, I'm using X in general to indicate data points. A single data point is a vector. Sometimes I will concatenate this data point with the scalar 1. So I'm going to denote this by X bar. Also, an entire data set, I'm going to denote this by capital X, that's bolded. Then capital X bar is going to be the entire data set that's now concatenated with a row of 1s. We have the output, which is Y. The vector of outputs for all the data points is going to be bolded Y. The number of data points in a data set is capital N, and the number of features is capital M. Okay, and then we talked about weights. So a weight vector is going to be denoted by W. When I use a transpose, it means that I take the row version of that vector. And in some cases, I'm going to add as well an initial weight W naught. And the reason for this is because this way, when I multiply W transpose by X bar, then I get W naught that is multiplied by 1. Okay, so that's the reason why I introduced this X bar notation, right, that will allow me to essentially talk about X with an additional 1 so I can just multiply this by W. Okay, any questions regarding the reference sheet? Okay, good, let's continue. Okay, so we've now defined the problem. What's left is how we're going to solve that problem, and then as we formulated it, right, we can solve this problem via optimization. So at the end of the day, to find the best linear function can be written here as an optimization problem where we're trying to minimize the Euclidean loss. So that's the squared distance, squared Euclidean distance, by varying the W's. And okay, so this is an optimization problem. Now this optimization problem happens to be an easy one because it is convex. Now when I talk about convex optimization, who knows what convex means? Oh, okay, we've got a few people, very good. Now for everyone, let me define what convex versus non-convex optimization means. And here we can do a parallel with P and NP. So in computer science, right, algorithms are tractable if they're polynomial, so they're in P, and intractable if they're NP hard. Right? Now, in optimization, there's a similar classification, and here convexity is what determines that a problem is easy, and then when a problem is non-convex, then it is hard, it is difficult. And then it has to do with whether or not we can find the global optimum reliably. And in fact, if we can do non-convex optimization tractably, there's a connection with NP hardness, which means that we could in fact solve NP hard problem tractably. So these things are linked. Okay, so let me draw on the board an example of a convex optimization problem. Okay, so whenever we've got a convex objective, it might have a shape that looks like this. This is a nice bowl shape. And if we're trying to find the minimum of this function, then it's pretty easy because there is one minimum here. And in fact, we can find this minimum by starting anywhere on the curve. So we could start here and then simply compute the gradient and then take a step in the negative direction of the gradient. So if I'm at this point and I find the negative of the gradient, take a step then I might end up here, measure the gradient again, take another step, end up here, continue, and eventually, right, we arrive at the minimum. So when we do convex optimization, a simple technique that does work reliably is to do gradient descent. You essentially just go downhill and follow the curvature of your function. Now in contrast, if we look at non-convex objectives, we might have, for example, a function that looks like this. So this is a curve that has two minima. There's one here, another one here. This one is known as a local minimum, and this one would be a global minimum. And the problem with this curve is that if I start here, and then I simply follow the negative of the gradient, and I make some steps, right, then I will eventually arrive at this local minimum. But then at this point, at this local minimum, the gradient is 0, so I've got nowhere else to go, and I'm stuck, right? And then it's pretty clear that where I want to go is this global minimum, but then there's a hill in the way, right? So myopic techniques like gradient descent will not be able to necessarily reach the global optimum unless we start in the right region. And here you might say, well, what about other techniques than gradient descent? The reality is that in general, for non-convex optimization problem, we do not have reliable or tractable techniques to find the global optimum. Okay, so there are better techniques than gradient descent, but still, in order to have some guarantees, generally speaking, there doesn't exist any algorithm that is tractable and will find the global optimum reliably. And this is where there's a connection with NP hardness. If we could do that, then we would have shown that NP hard problem can be solved in polynomial time. Okay, so now the problem that we're considering is of the type that's convex, so it has a shape like this. And in fact, our objective, because we're looking at Euclidean distance, it's a quadratic objective, so we can show that the loss function is really a quadratic function that has this nice bowl shape. Okay, any questions regarding those drawings? Okay, very good. Okay, so now I kind of mentioned already briefly that one way to approach this is that we could find a solution simply by finding the gradient and taking steps in the direction of the gradient. But there is in fact a more efficient and closed form solution for this problem. The idea is that we can compute the gradient. So here I've got my objective. So this is what I'm trying to minimize. And I can compute the gradient of this objective. And now, if I'm really looking for the global minimum or some minimum, there is a condition that we can use that is necessary for ensuring that it's a minimum. This condition is that the gradient should be 0. If my gradient is not 0, it means there's a direction in which I could keep on going down, and then I could improve my solution. Right? So gradient equals to 0 is a necessary condition, and then we can use that. So here we can set the gradient to 0, and now one nice property of convex optimization problem turns out that this condition is not only necessary, it's sufficient. So there exists a single point that will be with a gradient of 0, and then so if we solve for that, so in other words, if I find the W that satisfies this equation, then I will have my solution. So this should be intuitive, because if I look again at my drawings, right, at the minimum, right, the curve is essentially flat, so I've got no slope, so it's gradient 0, and then that's the only point that has that, the global minimum. So that's what I'm looking for. Okay, so when I form this system of linear equation and I want to find the W that satisfies this, now in this equation, if I treat W as the variable, then I can see that this is a linear equation because W only appears once. Now this is a little bit, yeah, here we have to be careful with the notation because traditionally X would be the variable, but then in this equation it's W that's the variable. X corresponds to our inputs, right? We have these values, so these are not variables, at least not in this slide. Okay, so W is the variable. So now, if I want to solve the system of linear equation, I need to isolate W, and I can do so by rewriting this system in the form of AW equals B. So here, the idea is that I'll have a matrix A that multiplies W and is equal to some constant B. So B is going to be a column vector. More specifically, A is going to correspond to this expression, and B will correspond to this expression. So you should be able to verify that when I plug A and B in here, then I get back this system of linear equations. Okay, so once we've got this written in the form of AW equals B, and we want to find what W is, the simplest thing to do would be just to invert A, and then that allows us to isolate W. So this is conceptually perhaps what is the simplest. Computationally, it tends to be faster, tends to be better to in fact solve the system of linear equations directly. So there are techniques like Gaussian elimination, conjugate gradient, and iterative methods that can be used to find the solution, and they tend to be faster and they have better properties often than computing the inverse. Okay? Now this course is not about linear algebra. Okay, so these topics are covered in other courses. So I'm just mentioning this, you know, for your own understanding. But in any case, you're not expected to know what is Gaussian elimination, conjugate gradient, and the iterative methods for this. Okay. Now for assignment 1, as we saw, there's one question about linear regression. I'd like you to code it from scratch, which means that I don't want you to use a package that already does linear regression for you, but then it's okay to use a package that does matrix operations, like computing the inverse or solving systems of linear equations. Okay, so this course is not about linear algebra, so you can use that. Okay, so let's draw another picture that will now illustrate how we're essentially finding a line that is going to be optimal according to our loss function in terms of fitting the data. Okay, so I'm going to redraw what I had here. So let's say that this is the line that we find, and that I've got some data points that are around the line like this. Okay, so the idea is that when I find a line that minimizes the objective that we talked about, we can imagine that for this line, the inputs correspond to the x-axis, and then the output would correspond to the y-axis. And here, I'm trying to minimize, essentially, the Euclidean distance with respect to the output, so that's with respect to y. So here, I'm trying to minimize the vertical distance between every point and my line. So you can measure, essentially, the distance by looking at those vertical distances. Okay? So intuitively, you see we're finding the line that will try to shrink those distances, which is the same as if for every data point, it's a bit like if I had a nail that was into the board, right? And then at that nail, I was going to attach a spring, and then this spring would try to pull a stick to be as close as possible to every data point. The problem is that when one nail pulls the stick in one direction, another nail elsewhere will pull the stick in a different direction, and then eventually this will stabilize at some location where the distances are minimized overall. So that's the intuition here. Okay, so here we can think of this as the vertical distance that we minimize. Yes? Sorry, say that again. Is there? Oh, can there be multiple solutions? So no, in this particular case, there is a single solution. So there's a single solution because, as I explained, our objective is convex. So it turns out that it's a quadratic function. And then whenever it's a quadratic function, it will have a nice bowl shape like this. And then there's a single minimum. So here, there's a single way in which the stick is going to stabilize over time. And then you can sort of like, initialize the stick in any way you wish, and then it will eventually stabilize at the point where the distances, the vertical distances are minimized. Yeah?
How about if we don't have the A inverse? I mean, it relies to the singular matrix. I think, for example, we have another X dimension, and all the points are in one line, so we have infinite.
Okay, so great question. So I guess, the question is about what if the matrix A, we cannot invert it because it could be singular or close to singular. So in fact, we're going to discuss this in a moment. And this is indeed an important problem in practice. Okay. Okay, so when we find the solution based on this least square objective, it turns out that even though there is a single solution, that solution is not stable, it's not robust. And what I mean by this is that we could perturb slightly the inputs, and then this will change obviously where the line is going to settle, what is the best line. And then ideally, we would like to see that if there's just a small change, an epsilon change in the inputs, that the line will change as well, just by a tiny bit, something related to epsilon. But we'll see in a moment an example where a change by epsilon can lead to a much larger change that is independent of epsilon. And then so in that sense, it's not stable, and then it can lead to some problems. Now, when this happens, it's often related to what we discuss as overfitting, right? Because if I make some small perturbations to the input, right, it means that perhaps there's some noise that creeps in. Maybe it's due to some measurement errors, that my data is not clean. And then I would like to find a solution that perhaps is not going to be impacted by this, right? And the problem is that this least square solution is sensitive to this noise, and in fact too sensitive, and in some cases will lead to some overfitting. Okay, so let's do two examples. We're going to start with the first example here that will illustrate how this approach that we discussed works, and then we're going to do a second one. We're going to perturb one of the inputs by epsilon. Okay, so for example 1, the matrix A will correspond to 1, 0, 1 epsilon times 1, 0, 1 epsilon transpose, which is equal to 2 epsilon and epsilon epsilon square. Okay, so the way I obtain this matrix, if I just go back a few slides, okay, so it's based on this equation here, right? So that's the expression I'm using here to compute A. Now, in the same way, I can use as well this expression for B, which will give us the following expression. So for B, we have 1 times 1, 0 plus 1 times 1 epsilon, which is equal to 2 epsilon. Okay, to compute the solution, I need A inverse. So A inverse in this case happens to be 1 minus 1 over epsilon minus 1 over epsilon, 2 divided by epsilon square. And W, our solution, is A inverse B, which is equal to 1, 0. Okay? So this gives us a first numerical example of how the approach works. Now let's consider a second example. And the difference between the first and the second example is what I've circled here. So I'm going to add epsilon to the target for the first data point. Okay, so the first data point in example 1 had a target of exactly 1. And then in example 2, it has a target of 1 plus epsilon. Okay, so that's the only difference. So it's a tiny change. And let's see what the impact is. Okay, so for example 2, A is going to be the same as before. So 2 epsilon, epsilon, epsilon squared. So the same as before because A does not depend on the target, and the target is the only thing that we changed. And then A inverse will also be the same as before. So 1 minus 1 over epsilon, minus 1 over epsilon, and then 2 divided by epsilon squared. And now what changes is B, which is going to become 1 plus epsilon times 1, 0, plus 1 times 1 epsilon, which is equal to 2 plus epsilon, epsilon. Okay, and then W, which is equal to A inverse B, will be equal in this case to 1 plus epsilon minus 1. Okay, so now we can see that just by changing the target of the first data point by epsilon, we obtain different W's. At some level, it's normal. If we change the inputs, the outputs should change. But now the question is, how significant is this change? So if I look at the first entry, 1 becomes 1 plus epsilon. That seems OK. But what is surprising is the second entry. We're going from 0 to minus 1. And here, this difference is actually quite significant because epsilon is really meant to be a small value. I could make epsilon arbitrarily close to 0. I could make it arbitrarily small. It could be something like 0.000000001. Right? And then it leads to a change here of 1. Right? So you see we have an arbitrarily small change that leads to a change that can be much larger in magnitude. So this is problematic. This should not happen. Okay, so to illustrate what has happened, I'm going to draw another picture which will help us see why this is happening. Okay, so let me go back to the board. Let's erase this part. Okay, so here I'm going to represent only the first, so x, if you recall in our problem, let me just go back. So we have two entries for x. There's 1 and 0, 1 and epsilon. Okay, so x is two-dimensional. But then, in terms of drawing things on the board, it'll be difficult for me to draw things in multiple dimensions. So I'm only going to care about one dimension. I'm going to care about the second dimension because this is the dimension that varies, right? So here we've got a 0. Here we've got an epsilon. The first dimension is really this constant 1 that we've added to every data point. Okay, so I'm going to ignore that first entry. So here, x1 is really the input, 0 versus epsilon. Okay, so for the first example, we had two data points. And let me put epsilon here. I'll put 1 here and 1 plus epsilon. Okay, so we have one, so I guess if, so I've got the x-axis, that's really the second dimension. And then here, the y-axis is going to be the target. So for the first data point, I've got 0, and then 1 plus epsilon for the second example. So 1 plus epsilon is here. So that's our first data point. And then the second data point is epsilon with 1. So I've got epsilon here, I've got 1 here. So now I can draw a line that corresponds to the solution that is found for this example. So this is the solution for the second example. In this solution here, we have a slope that is -1. And then the solution W is equal to 1 plus epsilon minus 1. And then this minus 1 corresponds to the second entry. Again, I'm ignoring the first entry simply to keep the drawing simple. Okay? Now, so this is example number 2. Example number 1, the difference is that the target is just 1 for the first data point. So I'm going to have something similar where I have the first data point here, and then the second data point is the same as before. It's going to remain here. So now if I draw a line that goes through those two data points, I get a line like this that is horizontal. So in this case, I have a slope that is 0, and then our solution, W, was equal to 1, 0, where the 0 corresponds to the second entry. Okay, so now it should be clear that what's going on is that you see our original data led to a horizontal line. Then we changed the target of the first data point, where the target was raised from 1 to 1 plus epsilon, but then that causes the line to shift and in fact to have a slope of -1. And here this happens in part because, well, we just have two data points, right? If we had more data points and then I was just changing the target of 1 point by epsilon, it probably wouldn't change much. The line would not change much. But I only have two data points, so if I change one, then the line does change. And the other aspect is that those points are very close to each other, right? So just moving 1 point by epsilon, right, because the second point is right beside, then it does cause an important change in the slope. And here you see it doesn't matter what epsilon is, I will have a change in the slope that will go from 0 to -1. Okay, so this is an example that illustrates what might happen when we don't have enough data, when there's also some noise in the data. And this is, I guess, an extreme case of overfitting. Obviously, in practice, we're going to have more than two data points, but then noise is going to happen. And then chances are we're going to be working in higher dimensions as well. So even if you have more data, if you're in higher dimensions, you can have a similar effect that happens. Okay, so then in that sense, the solution is not necessarily stable, and it might suffer from overfitting. Okay, any questions regarding this drawing? Okay, very good. All right, so now we need to find a way of dealing with this. And one approach that we're going to see, which is common not just for linear regression, but lots of models, including neural networks, is known as regularization. What this means is that we're going to add a penalty term that will try to constrain to some extent the type of solution that we're going to consider. So here we're going to add a penalty term that corresponds to essentially forcing the magnitude of our weights to be as small as possible. So you see, our original objective was to minimize Euclidean distance between the output and the target, but now we're also going to minimize the magnitude of the weights. So this kind of makes sense to some extent because from a numerical perspective, if we have weights that are very large, that are arbitrarily large, we might have some numerical problems with that. And then it's generally a good idea to just keep things near the origin. So therefore, weights that are small, weights that are close to zero, might be preferable. Okay. Now I must say that this is just some simple arguments that are intuitive, but they're not necessarily rigorous arguments. And then next class, we're going to see how we can, in fact, justify this rigorously from the perspective of statistics. So there's a principle, there's a good reason why this approach makes sense, and it should become more clear next class. But for now, let's just go ahead with this idea that here perhaps what we can do is simply try to keep the weights as small as possible. And here, just to clarify the notation, so when I write vertical bars like this, two vertical bars, that means I'm taking the norm of the vector. The subscript means that I'm considering the Euclidean norm, and then the superscript means that I consider the square of the Euclidean norm. Okay? So this really just corresponds to the square of the Euclidean norm of the vector. The other thing to realize is that I've got a weight, lambda, here, that is used to determine the importance of that penalty term. And then so in the assignment, this is a hyperparameter that you're going to optimize as well via cross-validation. So here, depending on the problem, it might be good to use smaller or larger weights. And generally speaking, this is something that needs to be adjusted. Okay, so with this penalty term, what is going to happen to our solution is that it will change in the following way. So before, we saw that we got a linear system of equations that was of the form AW equals B. Now we can see that by adding this penalty term, we'll still have a system of linear equations, but these equations are going to be of the form lambda I plus A times W equals B. How do we get this? The idea is that we have an objective here, and we can do the same steps as before, where we can compute the derivative, set it to 0, isolate W, and then that will lead to the following form. Okay, so I'm not showing you those steps, so this is an exercise that you can do on your own. Okay, so it's not difficult, it's the same as before. So you simply take the derivative of this, set it to 0, and then you should arrive at this expression. Okay, so for anybody who's familiar with linear algebra, this solution with respect to regularization has some interpretation in terms of eigenvalues. So earlier there was a question about can we necessarily invert the matrix A? And then numerically, in theory, well, numerically it's not always possible. In theory it's supposed to be, but then the problem is that some of the eigenvalues might be too small. So here, what happens is that whenever we simply minimize Euclidean loss and we do not regularize, then the eigenvalues of the linear system might be arbitrarily close to 0, and then taking the inverse might be unstable, might lead to arbitrarily large eigenvalues, and that might lead to the type of error that we saw. Okay? If you use Tikhonov regularization, which is what I just explained, then we essentially force the eigenvalues of the system to be at least lambda because of this term here. And then, therefore, the eigenvalues are bounded away from 0. Taking the inverse will not be a big deal. And then we're going to get eigenvalues for the inverse that are bounded above by 1 over lambda. OK, if you're not familiar with eigenvalues of linear algebra, don't worry. This is just an aside to explain as well from the perspective of linear algebra what's happening. And it's another way of explaining as well how, I guess, overfitting might happen. Okay, so it's related to these notions as well from linear algebra. OK, so now let's see what happens in practice when we use the regularization idea that I just explained. OK, so for this example, I'm going to let lambda be 0.05 and epsilon equal to 0.1. So when we have lambda I plus a, numerically, this is going to be equal to 2 plus lambda epsilon, epsilon, and epsilon squared plus lambda, which is equal to roughly 2.05, 0.1, 0.1, 0.06. And then if we take the inverse, so lambda I plus a inverse, this will be equal to 0.531 minus 0.885 minus 0.885 and 18.1416. OK. So for both example 1 and 2, A and A inverse are the same. Okay? Where they differ is in a computation of B. So for example 1, B is going to be equal to 2 epsilon, which is equal to 2 and 0.1. And this will give us a W that's equal to 0.9735 and 0.0442. In the case of example 2, we have a B that is 2 plus epsilon and epsilon. So that's 2.1 and 0.1. But then this gives us a W which is equal to 1.0265 and minus 0.0442. OK, so you see, we perturb the target of one data point by epsilon. Now, we also try to minimize the weights to some extent. So we have a weight lambda of 0.05 in front of our penalty term. So that means we're going to minimize the weights somewhat. And then as a result, we obtain solutions that are now much closer to each other. So you see the solutions used to have 0 here and minus 1 here. Now we have instead 0.0442 minus 0.0442. And here you can see that those values are much closer. And in fact, they're roughly, like the differences here are in the same order of magnitude as epsilon. So epsilon was 0.1, right? And now the difference here is also on the order of 0.1. I mean, it doesn't have to be exact or anything like this, right? But it's on the same order of magnitude. So here we obtain something that can reduce the differences in a way that is closer to what we would expect. So this is much more stable. Any questions regarding this? Yes.
For what kind of systems or problems will the perturbation be significant because of the trouble that we have to use something like this?
Okay, so regularization in general is going to be useful all the time. So we're going to see that overfitting is a common problem. There's always a risk, and then pretty much all of the time it will be necessary, if not very useful, to do something to try to mitigate overfitting. And then regularization is one approach for doing that. Throughout the course, we're going to see some other approaches to help with that. Yeah. Okay, so let's stop here. This was the last slide. And then next class, we're going to see now how we can look at these things from a statistical perspective.